nice to have an excuse to come to Paris, even though don't actually need an excuse to come to Paris. And I'd like to thank the organizer. I'm actually not even sure who the organizers were, but I guess Henri is part of the organizing team, and I guess Aslan, who I guess is exhausted from organizing, and Oasis is also out there. Okay, so it's great to be here. So, you know, I'm talking about coding. That's not very surprising, and I guess Henri yesterday had beautiful slides and talked about iterative codes and spatial coupling. So I'm going to talk about something a little bit different. And the other difference is that Henri had beautifully crafted slides, and I'm going to do it on the board. Okay, so we'll see. So now, what we're interested in is really the simplest case, and I want to do everything from scratch. So in general, if I have a sequence of codes, let's say length n, and I'm always going to talk about, so this will be codes. And typically, I always think about linear, and I think about everything to be binary. And for me, n will be the block length. And I'm talking about information transmission about the simplest possible channels. So I'm going to talk about very simple channel models. And most of it will be, you know, the binary ratio channel with some parameter epsilon. Sometimes I also mention a binary symmetric channel. But we can think of other ones. So this is simply the channel that either lets the bit through, or with probably epsilon, it will erase things. And so what we'll be interested in is whether, you know, such a code, of course, will have a rate. And I'll denote it by R. And what we'll be interested in is, the question is whether such a sequence of codes achieves capacity. And how do we, you know, prove that a sequence of codes achieves capacity? And essentially, the components that I'll be talking about is, I'll talk about thresholds. So I'll talk about that if we want to show that sequence of codes achieve capacity, then it better be true, and I'll say in a second what I mean, is that we'll see somehow a threshold behavior. And when I talk threshold with respect to channel parameter. So this means there better be, when I'm taking my epsilon here, let's assume, I'll typically always think of this, and I'm taking my epsilon parameter, and I'm going to think of a knob, and I'm going to turn it, then it better be true that once I'm talking about long codes, that there will be a marked difference in the behavior as I'm turning this knob epsilon, and that, you know, at some point when the epsilon is small enough, the channel is good enough, everything will behave nicely. But if it's large enough, we'll see a jump in the behavior, and I'll tell you in a second what I mean more with this. And then we'll talk about the area theorem and how this applies to everything. So this is a threshold behavior, and this will tell us something about where this threshold actually appears. So this has something to do where is threshold, or it will be useful for us where is threshold. And we can really think of this as a conservation law for codes. And I think the first one that called it that was actually Cyril, who is in the audience, Cyril Meillasson. And once I'll tell you about these components, then there's two classes of codes where, you know, this kind of program works very well. One are these spatially coupled, which I'm not going to talk about, because Henri did this yesterday. He had a different take on it. He has a very nice proof technique to show that spatially coupled codes achieve capacity. But I'm not going to talk about this, but you could apply exactly this kind of line of thinking, particularly the area theorem, to show that spatially coupled codes achieve capacity. But what I'll talk about is, you know, codes with sufficient symmetry. In particular, you know, we'll think about Reed-Muller codes, but there are many other codes, and we'll talk about when such codes, or why such codes achieve capacity based on these kind of considerations. Now, just because, you know, I might forget to mention people, let me try to do this right away here. So there are lots of people that I should mention for the various parts. So when we talk about thresholds, I'll mention results by Seymour and Tillich, and that I think was 99. Then particular Kalai and Friedgut, we'll talk about, and also Bourgain, and there's various papers in here. When we talk about the area theorem, again, there are several papers. There's one sequence of papers, in particular with Ten Brink and Ashikmin. So there's several papers around this, and Kramer. And that relates mostly to the binary erasure channel, which I mostly talk about. But then the kind of the way I talk about this will be really due to Cyril. So we have Meillasson, then Andrea Montanari, and Tom Richardson. So some joint work that we did. So that relates about the area theorem. And then for since I'm only talking about this part, so there are quite a few people involved. Of course, here is Henri. So there's a whole sequence. So we have Aaron, let's see, the alphabetically order. OK, there's Kudekar. Let's see, I have to figure out if I can still. OK, I think he was first. And there is a student of Henri is Kumar, Santosh Kumar. Then we have Marco Mondelli, who is also sitting here. OK, Mondelli. Then we have Aaron. No, we have you first. Pfister. OK. Then we have Aaron Sasoglu. And I was also involved. And in principle, this is a very nice story because there were really two groups, particularly Henri and his student. And then the rest was another group that I was involved in. But and this all happened while we were in Berkeley at the Simons Institute. And I'll tell you a little bit about this story later. OK, good. So now let me tell you, let's start a little bit with the thresholds. OK, so what do I mean? Well, typically, when we have a sequence of codes, then one of the main measures that we might be interested in is let's say, the block error probability, right? So this is the block error probability. And again, let's just think of the binary erasure channel. This is the length n. We have a sequence of code, block error probability, and we're having the epsilon here, right? And so now, of course, we could think of various decoding algorithms. Let's just think of the optimum one. It doesn't really matter so much which one we're thinking of, but most of them that we are interested in, even if we're thinking of the type of iterative that Henri talked about, have the property that those would be monotone with respect to the epsilon. OK, so when I'm thinking something where this block error probability is very natural, is monotone, meaning that if the channel becomes worse, then the block error probability would be increasing. So we would have some kind of curve. I'm typically going to draw boxes like this. This will be the epsilon, perfect channel, useless channel. And this would be perfect decoding, useless decoding. And we might want to plot this thing here. And so we would have some kind of increasing curve that we would have here, right, as a function for a particular n and as a function of epsilon. Now, if we're talking about a kind of threshold behavior, if this is monotone and let's assume continuous, then it does make sense if we have a delta, some delta, let's say between 0 and 1, that we define the parameter at which this block error probably hits this, hits this curve here, right? So I can define here an epsilon, and this, of course, will depend on n and of delta. And this is exactly that epsilon, right, such that the probability here for n and then that epsilon is again delta, right? And so I can do this for every delta. And so when we're interested in a threshold, what I'm interested in is what does the following function look like if I'm looking at the epsilon of n and 1 minus delta. and I'm looking at the epsilon of n and delta. Okay, so this one here is delta, and I'm looking here where it hits, let's say, 1 minus delta, right? So I have here epsilon and 1 minus delta here. Then what I will be interested in is like how long or how far is this transition here, right? So how long does it take to go between a very small delta, so think of delta being 10 to the minus 3, to a very large 1 minus delta, which is essentially 1. How long does it take this transition, right? And in particular, I'll think of about the sharp threshold if, let's assume we have a sequence of codes, and for every delta, okay, so for all delta bigger than 0, if it's true that in this sequence here, this transition will go to 0, right? And we might even talk then about how fast this goes to 0 as a function of n, perhaps, and we'll talk a little bit about this. But if this goes to 0, right, then essentially what we'll have in the limit, we'll have a picture in which we jump from 0 to 1 in some, infinitesimal like transition wave, right? And so that's what I mean that I'm talking about a sharp threshold. Now, there was a very nice result, and we'll get now to this one here, in which the first result, first major result probably in coding theory, in which people exactly talked about this kind of threshold behavior. So let me tell you, because it's a very beautiful and also a very general result, and it will connect quite closely to what I want to do. And this is the result by Tillich and Seymour. Sorry?
What decoding do you use?
So here, this is a general concept. The only thing, you can define this for anything. The only thing is we need that it's monotone. And, for this to make exactly sense, it's increasing and let's say continuous, then all these things are well defined. And you could have a sharp threshold. It could be Henri's iterative decoding that he talked about. Mostly we'll talk about maximum likelihood decoding, but it doesn't really matter from this point of view. Okay? So right now, the Tillich and Seymour result that talks about, so we have C with a code. It's going to be a linear block code. And we'll talk about the channel, which is either BC or the binary symmetric channel, so in which we flip. They have also extensions to more general channels, but let's stay with this. And so let's assume also the code C has a minimum distance. So this is the minimum Hamming distance. And in particular, they talk about map, so optimum MAC block decoding. So we take a linear code. Let's assume we transmit over the binary ratio channel. The code has Hamming distance D. Can be anything. And we're talking about map block decoding. Okay? And so they are then improved. So we have, again, this picture like this. Okay? And so what they prove is here is exactly is the following, that if I'm looking here at the n, at the, how do you call it, delta? So if I'm looking at how quick the transition width is, they prove that this transition width is smaller equal a constant, which is just a universal constant. And then the rest of the behavior is 1 over 2. Wait a second, I have to check it actually. Not sure now. What do they get? No, they don't have this. Okay. So this constant is just the delta. And let's just take this with square root of d. Okay, so they prove that this transition width is just of the order. So in this case, I don't specify now what this constant here is a function of delta. Okay, there's some behavior here much more explicitly. But the important thing for me right now is that this window here is of the order. If you look at this window here, So of the order 1 over square root of d. Okay? And so there are no assumptions are in code, right? And the only property that we've used as the code is the minimum distance, right? So let's see if this is a good or bad bound here. Well, I claim that this is a very, very good bound. Why, right? So just think of d. So think of a good code where d is, is some constant, okay, let's say kappa times n. Okay, so think of a let's say a very good code in which we can actually achieve a minimum distance, right? So if we have this here, right, then so I get things screwed up. Give me a second. Yeah, okay, it's fine. Okay, so if we have this here, right, then what it is, in this case, then we have that this thing here behaves like a constant over square root of n, right? But this is up to the constant here, right, which in their case is not optimum. That's the optimum scaling behavior, right? Why is this the optimum scaling behavior? Well, because even if I had an optimum code, right, even if I had an ideal code in which the behavior would be like this, as long as the number of, of erasures, right, as long as it's, I can do perfect decoding, right, up to the capacity. And then, if I have more errors or more erasures, I'll actually, can't. Just the variations of the channel, right, are of order square root of n, right? So if I have a block length of n, and now I have certain number of erasures in here, right, and I have an erasure probably epsilon, right, then of course the number of erasures that I get will be n times epsilon plus something, some constant, which is of order square root of n. Right? So even if the code themselves would be ideal, right, I could decode everything up to exactly what an optimum code could do, the channel itself will once in a while get me on the wrong side of the decoding thing, right? And this will be of order square root of n, right? And if we normalize now everything by n, then we see that this window can never be smaller than 1 over square root of n. Is that clear? Okay? So what in their case is of course, we know from the finite length behavior, so results by Strassen and Verdu and Polyansky, we know exactly if we were, let's say, at capacity by how this finite length scaling goes, okay? And that has exactly, again, this behavior with the square root of n, and we also know exactly what the constant in front of this is. Now, the constant, they don't get the right constant, but they do get exactly the right scaling of square root of n. Okay, so this is a very, very nice, very powerful result in which uses essentially nothing about, there's nothing about the code structure in here, which is only based on the fact that it has minimum distance. Yes?
Okay, so that argument of optimality, like that constant c does depend on epsilon, right?
Yeah, so
but here it doesn't, so is that...
You're talking about this one here?
Yeah.
Yeah, so, but if we're talking about if we're talking about capacity here, this will be simply a constant. Okay, there's nothing that vanishes or something like that. Will be a constant. And in terms of d constant, it's not optimum. Okay, so they don't get the optimum constant here, but they get the optimum scaling. That's what I want to say.
I just meant if there's an epsilon n, if the number of expected erasures is epsilon n,
right?
And the variation depends on epsilon too, right? It's like
yes, but that's true. But we're talking about, let's say, a rate and a half code. Okay. Then epsilon is, whatever, 0, depending if we're talking about the binary ratio channel or binary symmetric channel, it's a constant bounded away from 0. Okay, so there's nothing that diverges or anything. There will be a constant, but it will be fixed for the fixed rate. That would be the optimum thing, right? And so I think you have for the optimum scaling. I think for the binary, actually I'm not sure. It might be something like 2 times square root of epsilon times 1 minus epsilon or something like the constant. Okay, I'm not for the binary ratio channel. That would be the optimum constant. Okay, I might be slightly off, but roughly like this. But epsilon, think of it as a half right now. Okay, so there's nothing. Even if you have a sequence of codes, they all have to fix the same rate. There's nothing that diverges or goes to 0 or goes to infinity here. Okay. So this is a very, very nice result. There's only one little problem with this if we're talking about capacity achieving code. And that result is that it says that essentially any decent sequence of codes, or any sequence of codes where the minimum distance diverges, has a sharp threshold behavior. But unfortunately, it doesn't tell us anything about where this threshold actually happens. Okay, so we have no relationship of where this jump is with respect to capacity. All it says is that the code in the limit has a behavior in which it is perfect up to, essentially perfect up to some point, and essentially useless up to some other point. Okay, that's the only thing that it tells us. Now, you might wonder at this point. So we'll exactly trying to address now the issue of how we can locate this threshold, and that's where the area of theorem will come in trying to do so. But before we go to there, you might wonder about the following. Why do I even insist that for capacity of achieving code that I have such a threshold behavior, right? I mean, maybe I have some capacity achieving code, and I could have, behaviors something like this, right? Up to, all I'm interested in is that, let's say, up to a point which is the capacity I can do perfect decoding. And, why do I insist that it jumps up, right? I mean, it could just go up like whatever, some 45-degree line or something else, okay? Now, we know from the strong converse of the channel coding theorem that indeed, if we're thinking about the block error probability, it has to jump up to 1. Okay, so that's one way that once it jumps up, it will actually have to, above capacity, will actually have to jump up to 1. But we'll also see this today with a slightly different curve. It's not the block error probability curve, but it will also imply it for the block error probability curve, that indeed, and that's exactly where this conservation law comes in, that indeed it cannot be that you up to capacity are perfect, and then you have, let's say, some 45-degree one. Okay, so there's no loss that we're actually insisting that it actually has to jump to, if we think about the block error probability 1. Okay, good. So now maybe just one word about how to do it, or what the ingredient is. So in this, and also in the later results, the key will be an inequality that you can read up in the beautiful book by Gabor and his colleagues. Okay, it's Margulis-Rousseau. And so let me just explain, because anyway, the setup we'll need later on anyway. So let me just explain maybe a little bit what the setup is. And we think of the setup as the following. So take the Hamming cube and take a subset, sorry, of the Hamming cube. Okay, so let's take omega being some subset. So in their case, in here, what is this omega? Well, let's think of first the binary erasure channel. Then every erasure pattern is simply, you can simply think of a vector in 0, 1 to the n here. Okay, so maybe it's a 1 if there's an erasure, and it's 0 if there's no erasure, right? So the omega is simply a set of erasure patterns. Or if it's noise, then it's the set of noise patterns, right? And now what we can do is for every single erasure pattern, we can check whether or not we can actually decode or not, right? So let's assume we have the map decoder, as in this case. We pick a certain erasure pattern. We check, can we decode or not, right? And so this is an erasure pattern here. And let's assume that we cannot decode, right? We're making a decoding error. Then we simply put it in there. Okay, so this is the set of problematic noise patterns. Yes, so this is, sorry, yes, absolutely. Okay, so we're fixing, so C fixed and has length n, right? So I'm picking a binary linear code, I fix it, and now for this fixed code, for every either erasure or error pattern, doesn't matter, applies to both of them, I check whether or not a certain pattern I can decode or not, okay? And so here, something is important which implicitly are used, but might not be completely clear. For binary linear codes and symmetric channels, whether decode can decode or not only depends on the noise pattern, but doesn't depend on the actual thing that I sent. That, here we're using the linearity and that the code is symmetric. Okay, sorry, that the channel is symmetric. Okay, so it only depends on the noise pattern, independent of what the actual code word was that was transmitted. And these are the set of problematic words. So now, if that's a set of problematic words, then I can express this probability of error, right? So I had to call it first, I think, n epsilon, right? I can express it in a particular way as a function of this thing here, right? So let's assume I have an erasure with probability epsilon and non-erased probability 1 minus epsilon, right? Then I can have a natural probability associated to this. So if I have this, right, then the natural probability is this times the number of 1. Let me first write it down. So I just associate this Bernoulli product measure, right? So this is simply the number of ones, the weight, right? And so then the erasure pattern that has weight like this, right, has probability epsilon to this weight times 1 minus epsilon is just my notation for 1 minus epsilon times n minus this weight, right? And so then it's natural to simply, or it's clear that the error probability is then simply the following. So I go over all the patterns in my problematic set and I sum up their weights, right? That's simply the probability that I will make an error. And sometimes it's slightly more convenient to simply write this as this, right? Clear? So now in this Margulis-Russo inequality, so this function here now that we're always interested in, I can now simply think of mu of omega, right? And just to maybe make it more explicit that this depends on the parameter epsilon, I write mu of epsilon, okay? So I'm really, the epsilon goes here from 0 to 1, and as I increase the epsilon, right, this will be my error probability here. Okay, so now what does this inequality say? Well, what the inequality says is the following. We would like this to be, very steep here, right? And so this inequality, let me first write down, says the following. If I'm taking the derivative of this mu with respect to the epsilon, okay, then let me first write it down. Epsilon sum So what it gives you is it tells you an equality on the derivative of this function, okay? And I'll tell you now exactly what's on the right. And the idea will be that what we would like to say is that at least in some range, right, that this derivative is large. If I can prove that at least in some domain, once that this mu is not too small, this derivative is large, right? Then if I integrate it out, this will mean that this has to rise very quickly, and that will be the idea. Okay? Now, rather than, so a lot of it is this is only the starting point. This is kind of the trivial point, and I tell you, if you have never seen it, a very simple interpretation. But the more complicated part then, and that's where then the proof from Tillich and Seymour, and then the Calais, etc. comes in, is to bring that into a nicer form. That's where really the whole kind of the art is in there. And essentially what you want to show here is that the thing here on the left, or sorry, on the right, that this has some form kind of like this, that you have some kind of, that you can bound it by something like this. And this is the non-trivial part. So you want to say that the derivative is bounded by the product of the measured set itself and 1 minus, okay, times something, a constant here, and hopefully you can show that this constant is large. Okay, so for example, in the case of the Tillich result, okay, you will see here that there's the square root of the Hamming distance in here, right? So let's assume you could do this. Okay, I'll first have to explain you this, but let's assume you could do this, and let's assume there was an equality. Why would that prove the thing? Well, if you think of the curve, as long as this is very small, this right-hand side is also very small, right? So nothing happens. And if it's very large, close to 1, then it's also small because you have the x times 1 minus x in there, right? So as soon as the x is either small or large, it's essentially 0. But as soon as it takes on a non-trivial value, this thing here will be non-trivial, right? And if you have now a very large constant in front here, right, depending on the parameters, then you have a very large derivative, and this will mean that the function will very quickly rise. Okay, makes sense? Yes. I'll tell you. Okay, I've not told you. I've not told you what it is, and I will not tell you how to get there because that's a longer story, and this is, you know, there's some really nice and quite deep theorems in here. But this one is very easy to explain. Okay, so what does this mean? So think of the following. So rather than thinking of Hamming space, okay, let me cheat a little bit, but it's exactly the same thing. Let me simply think of, let's say, a two-dimensional plane here, right? So I'm not thinking of the Hamming cube here. And let me think of that, so this whole thing is the set 0, 1, just a picture to the n here, okay? And also here, I still missed one condition, which I'll tell you in a second. And let me think of 0, 1 to the n, and now let me think of a subspace here, okay, a subset here. So what's the subset that I'm thinking of? I'm thinking of a subset that it's what's called monotone, okay? And I need the monotonicity here is actually important, so this is only inequality if omega is monotone, and I tell you now what monotone means. Well, if this was a, let's say just in the real space here, all that would mean is that once a point is in omega, then any point that's larger component-wise has to be in here, right? And in Hamming space, it's the same thing. We also have a partial order, right? Where I simply component-wise pick the order, right? 0 is smaller than 1 component-wise, and that extends to a partial order on the whole vectors, right? So whatever, 0, 1, 1 will be smaller than 1, 1, 1, right? Because they're all the same here, but in this component it's smaller than that, right? So that's the partial order that I have. And so what then does this, so imagine right now, first I'll tell you in Hamming space in a second, but imagine right now that we had points in here, right? And what we're interested in is how much measure is in here as a function of epsilon, right? Now, the point is the following. As I turn the epsilon, these points will get different amount of probability, right? But you should imagine that there's essentially a flow that goes uphill, okay? Because the epsilon is increasing, means the erasure probably will be larger, okay? It means that points that have more erasures, namely points that are larger in this order, will get more weight as we're increasing the epsilon, right? And so what happens now? Well, if I'm trying to see by how much, if I'm turning the knob, this measure changes, right? Well, if I have a flow that's outside the set omega, it doesn't matter if I have, if the probability associated to this guy, if the probability associated to this guy, I don't include it, right? If I have probability mass that's inside and something, I think of a flow that goes up, again, it doesn't matter, right? Because it's already in omega. Okay, I will have now less here and more here, but it doesn't change the size of the measure of mu of omega, right? The only thing that matters is that when flow comes from the outside and goes into it, okay? But since I make small changes, the only thing that really matters is that the first time it hits the boundary of this point, right? They won't jump like right away inside, but the first time something flips and it hits the boundary, right? So these are exactly the points on the boundary, okay? So I'm only gonna look at what happens at the boundary. And so this is simply the measure of the point, we know. And so now the only thing, what is this thing here? So h of omega is the following. Okay, so it's 0 if this is not in the boundary. Okay, and if it is in the boundary, then it's the number of neighbors of omega in the complement. Right, so what is it? I'm simply looking at this, and I'm looking at how many guys are below me, are outside the set, right, and have neighbors. And neighbors here, I mean that Hamming distance 1. Yeah. Thank you. Okay. If it's not in the boundary, and if it's in the boundary, then it's simply the number of neighbors that I have here, and that's the multiplicity. So does the picture make sense? Now, you know, this to me is slightly easier to think in this real space here. But if you want to do this picture now in Hamming space, you simply have on the bottom. So you have partial order where you have on the bottom of this lattice you have the point 0, 0, 0. On the top you have 1, 1, 1. right? And now you simply do these, all the vectors. So this is the 1, 0, 0, 0, 1, 0, 0. So you take all the layers that have, so this is the point that is the all 0 point. Then you have all the points that have Hamming weight 1. And you simply connect them if they have Hamming distance 1. Okay, and now you do the one with 2. And then whatever the last one will be. Right? And so, of course, again, you connect them whenever they are neighbors. Right? And then the very top, there will be where just one is missing. Oh, sorry. And again, they will all be connected. Right? So you have each of them is a layer that has a certain Hamming weight, whatever, k. Right? And so now, to derive this, it's really very simple. Associated to each of these points, right? So if you take a generic point here that has Hamming weight k, then this has weight epsilon to the k times 1 minus epsilon to the n minus k. Right? And so now, how many neighbors does this guy have on the top? If he has already weight k, and this has weight k plus 1, how many neighbors does he have? Right, so how many guys are connected up to here? Yeah, I guess. N minus k, right? So it has simply n minus k neighbors here, right? And then you can go, so how many neighbors does he have down here? K, right? You can, so these are k. And so now simply take the derivative of, take the derivative of epsilon to the k times 1 minus k to the n minus k with respect to epsilon. You get two terms, one associated to this and one with a negative term associated to this, right? And you will see that these terms are exactly, you can simply think of these are the flows, okay? So you simply think if when you change things, you have a certain physical flow, certain physical quantity here, things flow up, and once you will get a multiplicity k, and once you will get n minus k, and one is exactly what corresponds to the inflow, and the other thing corresponds to the outflow, okay? And if you think about it like this, then this is, that's exactly what you will see that the equality is. Okay, so it's a very nice, simple geometric picture, and it's the starting point of all these inequalities. But the real hard part comes later on to show that this is related to this. And if you want to know this, you look in Gaber's book, okay, and you find all these relationships. So this is exact equality. So up till here, there's nothing. Okay, because it's exactly that all the flows here, it doesn't matter. All the flows doesn't matter. The only flow that matters is if you go inside here. Okay? Good. So we have the notion of, what's the time?
It is a little more than 5 till, and probably about 10 more minutes in this.
Okay, okay. Okay, so now we get to the second part. So just tell me when we're there. And okay. So now we get to the second part where we're talking about the error. So remember, so we know how to deal with thresholds. And the kind of technique that we'll be using will be something very related to this, just a slightly different, we start with the same thing, but a slightly different setup than what is in the Tilly. But the point is that so far, we still don't know where the threshold is. And for this, we need the area theorem. And as I mentioned, there was Ten Brink, Kramer, and Ashikmin, and then Cyril, who is here, and Andrea Montanari, and Tom Richardson, who, who relate to what I'm talking about here now. So the point is now the following. Very often we think things are, see things like good code, bad code, right? Well, things like this. And at least in the picture that I'll tell you here, the point will be that there is no such thing as a good code or a bad code, okay? This doesn't exist. They're only codes that have different characteristics, okay? And so what I mean is that there's a conservation law or something that stays preserved, and that's always the same and only depends on the rate. So rate will be the thing preserved the quantity. And the only thing you can decide is kind of where a code is bad and where a code is good. But overall, it's, if you think of the whole behavior of all channels, all the codes will do the same. So now, rather than starting maybe with the simplest case, let me do the simplest case still. So the setup is the following. So unfortunately, what is not true, which would have been nice, is if this conserved thing would have been this curve that we just talked about here, right? And what would have been nice is that for every code, if I'm looking at the probability of block error, that this area here would have been the conserved quantity, right? Because block error probability is something very natural, would have been quite nice if different codes with the same rate, right? So what I would like to have is that this, for example, was always the rate, right? If this was the case, then it could be, if I take now, let's say, codes of rate 1/2, right? Then I could maybe have a characteristic something like this, or I could have a characteristic like this, or I could maybe have a characteristic like this. But the area here would always be the same, right? And so in that sense, there's no good or bad code. There's just different shapes, and this might be of different utility for different applications. Unfortunately, this is not true. Okay, so this is not the right quantity. So we need a slightly different quantity to work with. But it will be, again, a very natural quantity. And for particular, it will be very natural for the binary erasure channel. And so, so in general, the setup is, again, I have Cn. Okay, I have the binary erasure channel. This is the block length. And so there's a very natural estimator. So I'm sending, so X is the code word, right? And then Y is maybe the observed quantity, observed word. And so there's a very natural estimator, right? Which is, let me call it here I. So for position I, and as a function of the observed one. So this is my estimated, so this is my estimate for bit I that was sent, okay? And let me do it also here. Well, let me just do it like this. Okay, so there's a lot of notation in here. So let's just try to see. Head just means it's my estimate. Okay, so it's the optimum estimator for bit I of the code word that I sent. Right, so optimum, it's because it's map. But I'm not allowed to look at the whole observation. I'm only allowed to look at the observation not including the I. So I have the X. I have the Y. Right, these are both length n. And so now I'm interested in bit I. I want to know what this thing is. Okay. But when I'm estimating the bit I, I'm only allowed to look at the whole vector without observation, without the actual observation in I. Okay, I don't see what we received in I. Okay, and I'm looking at this estimator here. Okay, so it will turn out that the right thing to look is exactly this curve. So if I'm looking now at the error probability of this decoder, okay, so that's, again, this will be a number between 0 and 1, right? Then this error probability, so again, I will have now, so this is called, for the binary erasure channel, it's called the exit function. Just for historical reason, it's called extrinsic. Extrinsic means that you're not allowed to look at the ith bit. That's what extrinsic means. And this is extrinsic information transfer. Okay, just for historical reason, has no other particular meaning. If we're looking at this particular curve, it will turn out that indeed, for any code, this here, the integral over this curve is equal to the rate of the code. Okay, and that will be the curve that we're looking at. And so, Henry, you tell me when I have to stop. Okay. So now that's quite easy to figure out for why this is the case. If you look at some very simple examples, let's assume we look at the repetition code. But rather than doing now an example with a specific case, what I want to do next is to show you why this is true, that this is an that this is a conserved quantity. So
5 minutes is exactly that time.
okay, so maybe I don't do the proof. I'll just tell you where we start. Okay, so I told you already the solution. Okay, so but how would we go about? Well, it turns out that it's actually very, very simple, So what quantity, if we're something interested in a quantity that's related to the rate, what quantity is natural related to the rate? Well, if I'm thinking of the code Cn, and I'm picking a code rate x uniformly at random from this thing here, right? And I'm thinking of this as a random variable, then very natural, this here, right? If I normalize it 1 over the block length, is equal to the rate, right? Because a code of rate r means it has 2 to the nr code words in there, right? And if I take a uniform distribution on 2 to the nr, right, I get the log of that, then I get nr, and I divide by n. This is, so the entropy of that is exactly the r, right? So that's very natural. So hence, you know, it's quite natural to think of the following. So let's think of this here, where the observation here is, let's say that epsilon is equal to 1, right? So if I think of the conditional entropy here now, I give you my observation, but let's assume the observation is for an erasure channel with erasure probability 1, then that's of course still, that's exactly the same as here. I haven't given you anything, right? And that's, you know, again r, right? But what is, if I'm looking at the following, if I give you h of x and y, and epsilon is 0, what happens if I give you this? Well, if I give you all the observation, there's no erasure whatsoever, right? Then I'll, of course, observe the vector itself. So that entropy is 0, right? So if I normalize now everything by 1 over n here, and I'm looking at this quantity here, then this is just the rate of the code. OK, so far so good. OK, so if I have this, but you know, these are, you know, and I want to relate this to an integral over epsilon, then what is more natural, okay, to simply take the derivative and then integrate it back out, okay? So what we're just saying is, trivially, just by definition, if I'm taking the h of x, y, epsilon over the epsilon, right, and then I'm integrating this back out from epsilon from 0 to 1, right, then I will get exactly this one here, right, on top again, and I get again back the rate, right? So that's very natural. That. Sorry? So this is the observation if I send it for a channel with erasure probability epsilon. Okay, so you send x uniformly at random from the code word. You observe y, which is the x erased with probability epsilon, right? And so in the two end cases, if epsilon is 1, you see nothing. If epsilon is 0, you see everything, right? And so, I mean, this is, you know, we just basically, this here will give us exactly that here, right? And this, we've seen that that's just equal to the rate. Clear? OK, so clearly, what we should define, OK, what we should define is that we should exactly have this. So let me just call it f of whatever, f of epsilon. So this should be the function that I'm looking at, right? If this is the function I'm looking at, then indeed this will have this area theorem, right? Well, it has nothing to do with the property of the code. So this is exactly the function I should be looking at. The only thing is that this doesn't seem, you know, it doesn't seem to have anything to do with an operational thing. I can always take the derivative and integrate it out. Okay, so what I still need to show, and I'll show it you after the break, is that this is exactly the error probability of this particular decoder, a decoder that sees everything except the bit I and tries to do an optimum bitmap about this. And so I've here still something more precisely. What I will show you is that if I'm looking at the average over all positions I over these things, this average one is exactly what I'm interested in, and is exactly what relates here. Okay? So this was for a particular bit I. If there's symmetry, they're all the same. If there's no symmetry, these might be all, you know, there will be different ones, but the average of this is exactly this curve. Okay? So we'll take a break, and after that, I'll show you that this is true, okay? And then I'll tell you what that means for finding capacity for particular codes. Okay? Thanks.